What if you took the biggest engine on Earth and just kept adding turbochargers to it? One turbo, then two, then 10, then 100. What happens when you push the laws of physics to their absolute breaking point? Can you create unlimited horsepower, or does everything just explode? Let's find out what happens when engineering meets madness. So, what exactly are we working with here? Meet the Wärtsilä RT Flex 96C. This absolute monster is the largest reciprocating engine ever built by human hands. We're talking about a machine that stands 44 feet tall and stretches 87 feet long. That's longer than a basketball court and taller than a four-story house. It weighs over 2,300 tons, which is heavier than 1,500 cars combined. And this beast produces 107,390 horsepower in its largest 14-cylinder configuration. To put that in perspective, your average car makes around 200 horsepower. This engine makes more power than 500 cars running at the same time. This thing was built for one purpose: powering massive container ships across the oceans. It burns heavy fuel oil, the thick tar-like stuff that's basically one step above liquid asphalt. But here's where it gets interesting. Right now, this engine is naturally aspirated, which means it's sucking in air at normal atmospheric pressure. But what if we changed that? What if we forced more air into those cylinders than they were ever designed to handle? That's where turbochargers come in. A turbo is basically a spinning air compressor powered by exhaust gases. The hot exhaust spins a turbine at incredible speeds, up to 250,000 RPM. That turbine is connected to a compressor wheel that forces more air into the engine. More air means you can burn more fuel, and more fuel means more power. It's like giving your engine bigger lungs. A typical turbocharger adds about 6 to 8 pounds of boost pressure. Since normal atmospheric pressure is 14.7 psi, that's roughly 50% more air getting crammed into the cylinders. And in theory, 50% more air should give you 50% more power. But that's just one turbo. What happens when you add a second one? Well, you might attract a couple of super fans, but don't worry about that. However, this is where things get wild. You could set up the turbos in parallel, where each one handles half the cylinders, or you could go compound, where the first turbo feeds compressed air to the second turbo, and the second one compresses it even more. It's like having air compressors stacked on top of each other, each one squeezing the air tighter and tighter. Imagine the first turbo takes that 14.7 psi of atmospheric pressure and bumps it up to 22 psi. Then the second turbo takes that 22 psi and cranks it up to 35 psi. Now you're talking about more than double the normal air pressure getting rammed into those massive cylinders. The engine that was already making 107,000 horsepower could theoretically be pushing 200,000 horsepower or more. But why stop at two turbos? What if you added a third one, then a fourth? Each turbo in the chain could multiply the pressure even further. 3 turbos could push you past 50 psi. 4 turbos might hit 80 psi. 5 turbos could break 100 psi, which is nearly 7 times normal atmospheric pressure. At that point, you're not just forcing air into the engine, you're basically trying to liquefy it. And here's where the madness really begins. If adding 5 turbos gives you that much boost, why not add 10, or 20, or 100? Picture this massive ship engine surrounded by a forest of spinning turbochargers, all feeding into each other in a complex web of pipes and intercoolers. The sound alone would be deafening, like a jet engine having a fight with a tornado. But before you start ordering turbochargers by the truckload, there's something you need to know. Physics has other plans. Every time you add another layer of compression, you're not just increasing pressure, you're also increasing temperature. And heat is the enemy of everything mechanical. Those cylinder walls that were designed to handle normal combustion temperatures are now dealing with something closer to the surface of the sun. The metal starts to expand, seals begin to fail, and bearings melt under the stress. But that's just the beginning of our problems. The real nightmare starts with something called compressor surge. As you stack more and more turbos on top of each other, the air pressure keeps building, but the flow rate starts to drop. It's like trying to blow through a straw while someone's pinching it shut. The compressed air has nowhere to go, so it starts backing up through the system. When that happens, the turbochargers begin fighting each other instead of working together. Picture this. Your first turbo is spinning at 200,000 RPM, trying to push air to the second turbo. But the second turbo can't handle the volume, so the air bounces back like a pressure wave. Now your first turbo is getting hit with a wall of compressed air coming backward through the system. The compressor wheel that was spinning smoothly suddenly hits this reverse flow and starts to stall, surge, and potentially explode. And when a turbocharger spinning at 250,000 RPM decides to come apart, it doesn't just break, it becomes a grenade. Those compressor wheels are made of hardened steel or titanium, and when they shatter, the pieces fly out like shrapnel at supersonic speeds. One failed turbo could take out the entire array, creating a domino effect of destruction. But let's say you somehow solve the surge problem. Maybe you install massive bypass valves and intercoolers between each stage. Maybe you use computer-controlled wastegates to perfectly balance the flow. You're still dealing with thermodynamics, and thermodynamics always wins. Each time you compress air, you're adding heat. It's not optional, it's a law of physics. Compress air from 14.7 psi to 30 psi, and the temperature jumps from maybe 70 degrees to 200 degrees. Compress it again to 60 psi, now you're looking at 400 degrees. By the time you've run that air through 5 or 6 turbochargers, you're not feeding your engine air anymore. You're feeding it superheated gas that's hot enough to melt aluminum. The intercoolers between each turbo stage would need to be massive. We're talking about cooling systems the size of buildings, with pumps that could drain a swimming pool in minutes. The plumbing alone would weigh more than the original engine. And even then, you'd still be fighting a losing battle against heat buildup. Here's where it gets really interesting though. Let's say you ignore all the warnings, throw unlimited money at the problem, and somehow build this turbo monster anyway. You've got your 2,300-ton engine surrounded by 100 turbochargers, each one perfectly controlled, perfectly cooled, pushing boost levels that would make a NASA engineer nervous. The first time you fire it up, something magical happens. Those massive pistons start moving, fed by air compressed to pressures that shouldn't exist in nature. The power output doesn't just increase, it explodes. We're talking about potentially 1 million horsepower or more, enough energy to power a small city. But here's the thing about unlimited power. There's nowhere for it to go. The crankshaft that was designed to handle 107,000 horsepower is now trying to transfer 10 times that amount. The metal starts to twist like a pretzel. The connecting rods, each one the size of a telephone pole, begin to stretch and bend under forces they were never meant to see. The ship this engine was supposed to power would need a completely new drivetrain. The propeller shaft would need to be as thick as a tree trunk. The propeller itself would cavitate so violently it would sound like underwater explosions. The ship might actually be too powerful for the water itself, creating thrust that the ocean can't handle. And that's assuming everything holds together for more than a few seconds, because at some point something has to give. So what's the answer to our impossible question? Could you actually keep adding turbos to the biggest engine in the world? Technically, yes. For about 3 seconds before everything turns into the world's most expensive fireworks show. You could probably stack 2, maybe 3 turbos before the laws of physics show up with an eviction notice. Beyond that, you're not building an engine anymore. You're building a very complicated way to turn metal into confetti. The real limit isn't the number of turbochargers you can bolt on. It's heat, pressure, material science, and the simple fact that at some point, the air you're compressing stops acting like air and starts acting like a liquid. The Wärtsilä RT Flex 96C is already a marvel of engineering at 107,000 horsepower. Trying to multiply that by 10 would be like trying to fit the power of the sun into a shipping container. But here's the beautiful thing about impossible engineering questions. They push us to understand the boundaries of what's actually possible. Every time someone asks what if, we learn something new about the world around us, even if the answer is usually explosion. And speaking of impossible engineering, what happens if you engine swapped a Prius with a Bugatti engine? Check out the video on your screen to see how fast things can really go when there are no rules. Thanks for watching.